Hello everyone, welcome to Stochastic Calculus for Finance 1. This is section 5.2 on the first passage of time, and we're doing the third part here. So if you remember last time we gave a definition of the first passage of time, and then we were studying some few interesting property. We showed this property first and demonstrated that why it's true. And now we're going to be focusing on this second property and later on this third property. So let's go on and actually show this, that the expected value of this tau m is actually plus infinity. Okay, so as a starter, I'm putting this thing here on the side so we remember where we're trying to get to go. And now we're going to talk about this theorem, which is going to help us actually prove this. Well, let m be a non-zero integer. Then, and the first passage of tau m for the symmetric random walk will satisfy the following property. And this is what we're saying that it will satisfy for all alpha between 0 and 1. So this thing kind of look weird, but as usual in this chapter, we see that actually this thing that looks kind of weird, this theorem that looks kind of random, will actually help us show the property that we're interested in. So let's go on and show that. So first, remember about this. We know that this expression here is true. And if you're wondering where this is coming from, well, we have just seen that the last video, right? If you remember our game plan that we had, we know that this expression here is true. The expected value of this process stopped at tau m is equal to 1. And since it's true for any n, then it's true for a very large n, in particular when n tends to plus infinity. And we have also shown this thing here. So, and what you can note here is like why we have m here and this m tau m is because in the case where tau m is less than infinity, right? Because otherwise, like if tau m is infinite, then we're just multiplying by 0, so we don't have to worry about that. But if tau m is less than infinity, then we have shown also that this thing is just going to be m. That's all that I can say. And if you just double check the video, the previous video, make sure to watch that so that you can follow up here. So this thing is really simple. So we know that we have seen that. So, and because we know tau m is less than infinity, we have proved that, right? Sooner or later, the symmetric random walk will hit the level m. So the stopping time is less than infinity. We know that. So that means that there is not really need for this indicator function. We know this is true. We know this is going to be always 1, right? So we can just simplify this expression by removing this, since this is always 1. And that's exactly what we do in the next step here. Now, if you now you have two terms that we will be paying attention. There's the orange term here, and there's the blue term. So let's start by this. So how about we can call this any random variable? We can call it x, we can call it y. Let's call it alpha, right? And if you pay attention, you will see that, well, alpha works because what we want is alpha to be between 0 and 1. And if you pay attention here, then you'll see that this alpha, defined this way, will always be between 0 and 1. So we're good there. So now we can do some crazy math, some algebra, so that we can try to express this guy as a function of alpha. So we're going to do some extraction, multiplication, and all that stuff to try to extract this thing as a function of alpha. And after all this math, and to solve this, we can use some simulation, symbolic math using Python or some other symbolic math or softwares. Or you can just do it by hand if you're good at algebra, long tedious algebra. But at the end of the day, this is what you're going to have. And so we have that. So we can do some just replacement, right? So we have this e to the power sigma. We have what the e power sigma represent. We can just plug it in here, replace that. And same thing for alpha. This whole thing is just alpha, so we can just replace it by alpha. Okay, that's what we have here. And we know this is equal to 1. So this is like a good start for us. So now what we can do is just take the term that is not random. So if you pay attention, you would see the random variable in here. The only thing that's random is actually the store m, right? Because that's our random variable. So this is actually a constant. All this thing is a constant. So what we can do, you can take it out, and we take it out and then move it to the other side of the equation. Then we'll just exactly get the property that we're trying to show. Okay, so with that, we know that this is true. So what can we do? Well, so the next step, let's just, instead of trying to work with the expected value of tau m, this guy, let's just try to find, let's just start by showing the expected value of tau 1 is equal to infinity. And if you remember what these stopping times are, it's just basically you have a random process and we pick level 1, right? And the random process is going to do what the random process does. But then this tau is going to be the very first time it's going to, tau 1 is the very first time the process is going to hit level 1. So nothing too mysterious about what we're doing here. So let's show that the expected value, the expected time that's going to hit level 1 is actually equal to plus infinity. Well, to start, we have that this guy, right? And nothing mysterious. We're just taking here everything we see, everywhere we see m, we replace by 1. Very simple stuff. Then what we're going to do now is take the differentiation. We're going to take this and differentiate this side with respect to alpha. And we're going to take this side and differentiate with respect to alpha. That's all we're doing here. And since this is like an exponent, it's going to come down and then just going to have a -1. This is just a basic rule of differentiation. And on this side also, you can do some differential with respect to alpha. Again, you can use a symbolic math software, or you can do the tedious differentiation by hand. But at the end of the day, this is what you're going to come up with. All right? So if you pay attention now, like what we want to show is the expected value of this tau 1. So this tau 1, we managed to bring it down, right? So the tau 1 was at the exponent, but by taking the differentiation, we managed to bring it down. So now we just need to somehow find a way to get rid of this term, and we'll have the expected value of this tau 1. So the way we can do it is basically we can take the limit as alpha. The lim as alpha tends to 1. And why we're doing that? Because, well, we cannot quite set it to 1, but if it's very, very, very close to 1, then whatever it is, that thing is, you take to the power of I don't care what, you're just going to get 1. And 1 times tau 1 is just tau 1. So that's what we're trying to do here. That's why we're taking the limit. Or a number that's extremely close to 1. Right? So that's why aka the limit. So by doing that, we'll find actually this expression. And so naturally, this is just like 1 to the power of something. We don't care what that thing is. It's going to be 1. So great. So now we managed to get rid of this term because that's what we're trying to show. So there's this infinity now. So we're saying that if we take this limit as alpha tends to 1, we're going to get plus infinity. And to show this, we can do again some complicated math, or we can just plot the function and see how it behaves when we're getting closer and closer to 1. And that's exactly what I did here. Let's look at this function. So this is the function. I'm just replacing alpha by x here because that's what this website, this graphic calculator needs. And by taking the graphic calculator, we can see that this is 1. And as we're getting close and closer to 1, then this thing is tending to plus infinity, right? So that's where this plus infinity is coming from. I know this is not the most rigorous mathematical proof, but I think it does the job to just show exactly and make sure we understand what's happening here. So then we managed to prove that. So good news. And now finally, the final thing we need to look and understand to be able to prove our final property is that you can notice that tau 1 is going to be less than tau 2. The stopping time is going to be less than n. And the reason is, again, I think it's very obvious. I probably don't need to talk about this, but let's say this is the level 1. This is the level 2. This is the level 3, right? So tau 1, so the first time the stochastic process is going to do what stochastic process does. And when it reaches level 1, boom, that's our tau 1, right? And then it's going to continue doing what it does. In the first level, it reached level 2. That's going to be our tau 2. And if you look, then tau 2 is always going to be larger than this tau 1, right? Because there is no way that this thing can reach level 2 without before somewhere in the past reaching level 1 already. So that's why this thing just holds. So if tau 1, the smallest one, is actually infinity, then you can imagine that everything else is going to be infinity, right? So, and that's all there is to it, really. Then we can, that's really why we can say this is true for all m non-negative integers. And again, since we know the expected value of tau m, since this is talking about symmetric random walk, that is also going to be equal to the expected value, right, of tau minus m. It's just a property of symmetric random walk. All right, so I think that was like the very big thing that we wanted to talk about here. We have shown essentially the second property. So next we're going to try to move to this third one. All right, thank you very much for watching, and if you like the video, please subscribe and like. It helps me a lot and keep me motivated. Thank you and take care.